Hello and welcome back. Let's talk about surface areas. So in the past two videos we've talked about revolving functions around the x-axis, and we've also talked about arc length. Now let's talk about putting them together. What is this that I speak of? This is, of course, surface area of revolution. So if I was to take this function and wrap it around the axis like that, and I wanted to know the surface area of this, how would I find that? Well, let's use the same intuition that we used in the past few videos. Past two, sorry. So we've got a little section on the curve, and we found out last video that that is ds, a small section of arc length. And so our little tiny slice here that we also talked about, it has a circumference that depends on this. Well, it's got a circumference, but then that also makes an area with a width ds, which is technically infinitely small. So we can call this circumference. We know circumference equals 2 pi r. So this means that the circumference as a function of x, as we talked about, has to be 2 pi times the function of x, because the function of x depends on x, and so the circumference as a function of x is just 2 pi times the radius, which is the function, of course. So that's our circumference as a function of s. Now the area of this little tiny function, so a little tiny area, we'll call this a d big S equals 2 pi times f of x ds. So small size of our rotation area, ds, capital S, is equal to our circumference times our small area, ds. That's like the volume of a cylinder almost, or a surface area of a cylinder. Just the sides, of course, not the circles on top. So if we integrate both sides, we're going to get the integral of ds, d capital S, that's just going to give us capital S. So our surface area, our total surface area, equals, we can take this 2 pi out, 2 pi integral f of x small ds. What's the small ds? Well, that's root 1 plus dy over dx squared dx. And that's how we get our formula. This is how we can think about it. And I think it's very smart to think of this little ds term, because it makes you not or understand where this comes from. So everything is based off of this idea of an integral. We can do so many things with it. I just love. So let's use an example. We're going to have to use simple examples again because we haven't gotten into our integration techniques just quite yet. But let's use the example of y equals x again. There's our example. So we know our s is going to equal 2 pi. Let's take the surface area from 0 to, well, what do I have here? 0 to 3. 2 pi integral from 0 to 3 of f of x, which is just x, times root 1 plus dy dx is just 1, squared is also 1, dx. So we can take this root 2 out. So this equals 2 pi root 2 integral from 0 to 3 of x dx, which is 2 pi root 2 times x squared over 2 evaluated from 0 to 3, which is just 3 squared over 2. So our 2's cancel. We get 3 squared pi root 2. Our surface area is 9 pi root 2. How amazing. That is surface area. Let me make sure I got the right answer. That's correct. We can double check it with a cone, evaluating the surface area of a cone. You will get the same thing. I evaluated it just before I did this video, but if you'd like to do it yourself, go right ahead. But with that, thanks for watching. I hope to see you guys all in the next video, where we will be talking about trig integrals. So, fun stuff, figuring out how to evaluate some more integrals. And yeah, hopefully becoming much smarter people, which is everyone's goal. Anyways, see you in the next one. Thanks for watching.